In this segment, we look at some examples of three-dimensional quantum systems, which are all generalizations of one-dimensional systems that we have studied before. We start with the free particles, so the case where the potential energy vanishes. The Hamiltonian then just involves the momentum operators, which combine into the Laplace operator. So the solutions will be momentum eigenstates. We can check this by taking the derivatives in the Laplace operator, or purely algebraically as we did in one dimensions. And the energy is then related to the momentum eigenvalues p in the same way as for a classical free particle. Now in one dimensions, the most general solution was a superposition of the two counter-propagating waves, which have the same energy, hence are degenerate, but in three dimensions we have a much larger choice. As mentioned before, a single plane wave factorizes into three one-dimensional functions. Now this factorization turns out to be a very useful guide when we look for other models for which we can find exact solutions. For instance, let us assume that the potential is really the sum of three separate functions of the three different coordinates. Then we can use the method of separation of variables to reduce the system into three one-dimensional ones. For this, we write the wave function in terms of three corresponding factors, just as we had for the plane wave. And then we insert this into the Schrödinger equation. When you divide by the wave function in this separated form, you have the energy on the one side and three different terms that only involve one coordinate each on the other side. But as the energy itself is a constant, each of these three different terms must be constant too. We call these constants Ex, Y, and Z, so the energy will be the sum of these three constants. And looking at each term separately, we see that these are really three one-dimensional Schrödinger equations with a corresponding potential. So you can simply solve these three one-dimensional Schrödinger equations and then freely combine the solutions into the wave function psi, with the energy being the sum of the energies from the three different problems. I will illustrate this immediately for the particle in the box, but the following remark will be useful when we want to extend this idea further. For the plane wave, the wave function was the product of momentum eigenstates. So note that it is now the product of the eigenstates of three one-dimensional Hamiltonians. Now these three Hamiltonians commute with each other as they involve different coordinates, and they then also commute with the Hamiltonian itself. Hence you can look at them as a complete set of simultaneous observables. So having such a complete set that commutes with the Hamiltonian will generally be useful. And it turns out that this is often arising from symmetries. I mention it already now because we will soon use this when we discuss angular momentum, which is linked to rotational symmetry. Okay, so to illustrate this method immediately, consider that the particle is confined to this box here, with sides of lengths Lx, y, and z, and hinged to the origin. We can indeed write the potential as a sum of three separate ones, as shown here. Note that this ventures only inside the box and is infinite outside. In some regions of space that's a sum of infinities, but that's certainly all fine. And at the end, this is of course just taking the limit of a very large potential. Now we know the solutions of the one-dimensional problems already, so can write them down immediately along with their energies. So the total energy is a sum of these energies and the corresponding wave function, the product of the individual wave functions. Importantly, we can combine these solutions freely. The three indices n, x, y, and z are all independent of each other. In this context, we call these indices quantum numbers, and that's because we can use them to label all states. For convenience, we collect them into a vector, as shown, and then simply attach the indices to the appropriate wave function. Just to mention, you also sometimes hear the word good quantum number. That's often used when these quantum numbers arise from a symmetry, because they are then typically also related to a natural observable of the system. And again, we will see this soon for rotational symmetric systems, where the observable in question will be angular momentum. One of the main uses of quantum numbers is to see how many states have the same energy and how these states are distributed over energy in general. That's sometimes the most important information, say in the context of thermodynamics and statistical mechanics. We will discuss such physical implications in detail for the problem of black body radiation, with which we will close the course, but it is also relevant, say, for the heat capacity of a solid. Now, in terms of states sharing the same energy, that's what we call degeneracy. And it occurs, for instance, for the particle in the box when we equate all side lengths, so make the box a cube. The energy can then be written a bit more compactly as shown, from which we see that it only depends on the squared length of the index vector. So, for instance, we can find 6 states for which the squared length is 14, as shown here. To keep track of this degeneracy, we introduce the degeneracy factor G, and here for this state it is just 6. And in terms of how the states are spread out in energy, we introduce the so-called density of states. That's a sort of smoothed out densities of the levels, so similar to giving a density to a gas when it really involves individual atoms or molecules. And the density of states counts these energy levels, including their degeneracies. Therefore, we use the word states in here. We can find this in 3 steps. First, we count the number of states up to a given energy. Then we smooth this out. And finally, we take the derivative of this smoothed out number of states, and this is then our density of states, rho of E. Sometimes we combine steps 1 and 2 by using a reasonable approximate way for the counting, and that's indeed what you would do for the particle in the box. For this, think of the space where the vector n lives. With its integer indices, it really sits on a 3-dimensional lattice in this space, with one state on each lattice point, provided that the indices are all positive. Furthermore, the spacing of the lattice points is just 1. So if we fix the energy, this fixes the length of n, and all states with energy up to the specified value are inside the corresponding sphere. The approximation is then to just replace this number by the volume of the sphere, divided by 8 to account for the requirement that all the three indices are positive. Now you can read the relation between energy and n backwards and express this in terms of the energy, which gives you the already smoothed out number of states. And finally, we take the derivative to get the density of states. So this is our final result. As shown, it is simply proportional to the volume of the box, L cubed. So it is useful to extract the factor in front of this, which we call the local density of states and denote as nu. Well, the density of states, of course, depends on the problem, so there are some interesting variants. For instance, we see that our final expression for nu depends on the mass of the particle. In a semiconductor, the motion of the electrons is modified by the interactions with the atoms in the crystalline lattice, as well as by the interactions between the electrons themselves. But in perturbation theory, you can describe them as essentially free particles with somewhat modified properties, including an effective mass. So this effective mass would then enter the local density of states and thereby also determine the thermodynamic properties of this system. Secondly, the result depends on the dimensionality of the box. You could confine the electrons using a suitably patterned device so that they can only move into one or two directions. And this changes the energy dependence of the local density of states. The key point here is that the higher the dimensions, the more closely spaced the states become on average as you increase the energy. For completeness, let me mention that this is the local density of states coming from the orbital motion only. The spin of the electron, which we soon will describe, doubles the number of states, so there is some extra degeneracy coming from this intrinsic degree of freedom. Next, we can also carry this out for photons, where we have to account for the different relation between energy and momentum. So this only enters at the point where we convert the length of the vector n into the energy, and in 3 spatial dimensions gives you the expression I state here. Again, this is for the orbital motion only. Photons have a polarization, so again there would be an extra factor of 2 from the resulting additional degeneracy of these states. Now this is what we are going to use in our discussion of black body radiation later on. And finally, to give you a more contemporary example, in graphene the interactions of the electrons with a 2-dimensional honeycomb lattice of carbon atoms gives them an effectively vanishing mass. That's to say, they have a relativistic energy-momentum relation similar to photons, but in 2 dimensions, and with the speed of light replaced by the so-called Fermi velocity. By following our steps, we then find the given local density of states from the orbital motion that we discuss here. While there are now 2 extra factors of 2 arising from the electronic spin and the so-called pseudospin or valley degree of freedom. So an extra factor of 4 altogether when we take these additional intrinsic degrees of freedom into account. As our last simple example, we consider the 3-dimensional version of the harmonic oscillator. We consider the so-called isotropic case, where the angular frequencies in all 3 directions are the same. This is not required for our separation of variables in Cartesian coordinates, but bridges over to the case of rotationally symmetric systems that we discuss next. So we can split the potential into 3 parts, as shown, giving us 3 copies of the 1-dimensional oscillator that we solved before. We then take these known one-dimensional solutions with equally spaced energy levels and corresponding wave functions and combine them as before. I want to focus here on the energies, so only write these out explicitly. There are again 3 independent quantum numbers, n, x, y, and z, which are all still integers, but now each starting at 0 instead of 1. So in the ground state they all vanish, and the ground state energy is now 3 over 2 h bar omega, just 3 times that of a one-dimensional oscillator. Furthermore, the energy only depends on the sum of the quantum numbers, and so you can find different combinations giving the same energy. This results in a degeneracy factor G as given here. From the expression of the energy in terms of the quantum numbers, we can also work out the density of states as given here. Note that there isn't a volume in here, and it would indeed be a bit difficult to define this based on this potential, so it does not make sense to introduce a local density of states. I also give the results in 1 and 2 dimensions. In 1D, this is simply the inverse of the level spacing h bar omega, given that the states are equidistantly spread out. This completes our discussion of the 3-dimensional harmonic oscillator. To motivate what comes next, I want to make the following observation, namely that this problem is rotationally symmetric. The potential energy only depends on the distance to the origin, not on the direction from it. We call such potentials central potentials, and the Coulomb potential would be another example. This is what we will have to study for the hydrogen atom. Now, the Coulomb potential cannot be written as a sum of 3 separate parts, so we will have to proceed differently. Well, classically, the motion in central potential simplifies when one utilizes that angular momentum is conserved. Indeed, what we will see next is that angular momentum occurs naturally as an observable when we try to solve these rotationally symmetric problems quantum mechanically.